Okay. Yeah, so today my topic is going to be about building time series predictive models at Convect AI, how we utilize Kubernetes and Kubeflow, try to automate this process as much as possible. I put a boring here. So it's, yeah, we put the boring here because we want people who are building these models feel like, okay, this can be a very systematic and organized way of doing things. So you don't need to kind of struggle a lot in building those models. Let me, all right. Yeah, so first thing about Convect AI. So this is a company that I'm currently building. So Convect AI is operations data platform company. So we call ODP. So ODP is very much like CDP. Some of you might know, like customer data platform, like Segment. So where you got all those kind of customer tracking data from different platforms, and you standardize those data into standard schemas and send them for downstream applications. So ODP is pretty much the similar idea. You've got all those data from multiple channels. So if you are a retailing company, if you sell on multiple marketplace platforms, and if you run your own sales channels, you have your own ERP data, then you get all those data into the standard format. And then you have a downstream applications like demand forecasting, inventory control applications, network applications, and or you can have some customized application built upon those data. So this is a platform which trying to kind of help enterprises to utilize all those operations data that you have and spread across different channels and make them into a standard format so they can be used for downstream application. So this is what Convect AI is doing. And today I'm going to mostly focus on this particular application of demand forecasting. We think demand forecasting is an interesting topic because it is very universal and it appears almost in any useful decision application as the first step. So whenever you want to make a decision or you want to decide something that is useful, the first thing you would like to do is that you're trying to quantify, trying to kind of estimate what your input will be in the future. So first thing, let's talk about why we need a framework to actually build a time series predictive models. So why can't we just have data scientists do their jobs and utilize whatever third-party libraries that are out there and trying to do this job? So the first thing, as I mentioned, the time series predictive models is very universal and common, especially in the retailing, manufacturing, and operations space. So if we think about the problem, the different characteristics about the time series predictive models, there can be different types of entity types. So it can be different things that you want to forecast. You can forecast the orders, sales, sales through rate, traffic, dollar amount, about different types of things. And there are granularity of your predictions. It can be at product level, store level, warehouse level, region level. It can be different horizon and frequencies. You can have your hourly data, daily data, weekly data, monthly data, quarterly data. And a business requirements can come as any point in this kind of like a high dimensional space. So it can be some long-term finance planning, which requires like a quarterly finance data at a region level. It can be some short-term product level sales forecasting, which comes at product level at a daily basis that can be used for operations. So because of the high dimensionality, the number of or the possibilities of problems that come into play is a very large kind of a space. And also there are other dimensions like if you want your model to be a point estimate or interval estimate, do you want interpretability for your model? Do you want to do multi-step estimation or you just want to aggregate this on? So we find out that like actually when our customers approach us, their problem can be any point in this space. And our data scientists are very struggle to kind of figure out, basically they are doing the similar type of thing, but with some like small variation, trying to kind of figure out the solution for different types of flavors of the same problem. So this is why we are motivated to say, oh, okay, things like we are doing the similar thing with small variation repeatedly. So why don't we have an automated and systematic way of doing that? So this is why we want to build a framework around the building a time series predictive models. Yeah, another important factor that motivate us is actually building a correct time series predictive model requires a lot of work. So for example, there can be different modeling strategy you can choose. So the predictive models can come into different flavors. For example, you can have like a single series problems where like each series are more or less independent with each other. So these problems can be tackled well with some traditional time series like models like ARIMA, moving average. And there can be times that there are multiple series actually come into play, and those things are highly correlated with each other. So for example, if you are talking about a product sales volumes across a company's sales channel, then there can be products that come in with the same category and they are highly correlated to each other. So under those scenarios, it might be beneficial trying to look at those things together and have one model to do your forecasting instead of treating them as independently and having two array models for each of them. And there are another issue of a matrix selection. So sometimes the correct way to quantify the accuracy or the goodness of your model is not so trivial. So there can be like the normal situation where you have kind of like a white noise type of series, then like a traditional regression type of metrics like RMSE and MASE. These are good enough for those type of problems. But there can be some long tail product sales volumes where you have most of the time the sales are just a zero, and there are some times where you have some positive sales volumes. But if you apply RMSE and MME, those kind of things, essentially you are getting going to be a zero, these things are like a very sensitive to the quantity volume of the time series, so these are not going to work. So how do you choose a good metric for your model is actually a very trivial task. And also there comes into play, if even like you decided what metrics you want to use for your model, when we are looking at putting time series models into production, the robustness of the model is actually very important. For example, we just talk about, usually like people are just talking about how do you select a metrics which quantify the accuracy of your model. But in reality, we see people are also caring a lot about the bias of your model. Are your model under or over prediction, your actual realization? And what's the error variance look like? Do you have like extreme bad behaviors or extreme worst performance on some of your products? If that's happened, is this going to affect your business? And also we are talking about the stability, both for the metrics and the forecast. So for example, if you are applying your model to multiple data sets at different time periods, is your model going to behave in a consistent good way, or it's going to vary a lot depending on the distribution of the data? And also the stability for the forecast. If you adjust the sum of the parameters or some input channel of your data, is your output coming from the model going to vary a lot? If you, let's say, if you adjust your price for just a little bit, does that kind of like put your sales volume to rocket high or not? If that's going to happen, then you better need a reason to explain to the business why these things is going to happen. So as we can see, so there are a lot of tricky things to decide. And on the more technical side, when we are developing models, unlike I would say like a traditional classification problem or regression problems, because of the factor of the time coming into play in time series predictive models, it's very tricky to do the backtesting. So you need to do the cutoff. You need to make sure the information come into your model is not going to be leaked from the future time. So you need to figure out the way to kind of prevent the information leakage. When you are searching for the parameters and evaluating your models using cross-validation, so unlike a normal k-fold cross-validation, you need to do a very specific, very much like what you do with the backtesting. You need to make sure those information are not leaked from the future. You need to do time series-based splits. And also there are different types of features when you are doing the feature engineering. There can be categorical, real unstructured features come into play, and these things can come in as a static or dynamic, depending on whether these things are going to change over the time. And also you need to figure out if those kind of dynamic features are going to be observed at your cutoff time. So this is trying to prevent information leakage as well. So there are many types of features, and for each of them, you need to figure out the right way to kind of process those things into something useful to your model. So yeah, so as we can see, this is a lot of work and trying to get everything right when you are building the model. And also we meet the situation where you have a lot of data or large volume of data come into your model. So for example, actually there are a lot of potentials that actually can be paralleled when you are building the model. So for example, when we are talking about the stability or robustness of a model, it's pretty common that you're gonna given a time series, you're gonna do multiple cutoffs, and they're trying to kind of get like multiple data sets. And then you're trying to kind of build your model and get a matrix on each of them and trying to evaluate the variation of your matrix. And these kind of like jobs can be more or less done independently, and later those results can be combined together. This is one way to kind of parallel your execution of the model. And another thing can be parallel is when you are doing this feature engineering. So one common thing to do is that you're gonna derive a lot of features given a time series. For example, you can look at the statistical distributions, the mean, the variance, the mean of the series, the number of peaks. These things are more or less can be done independently as well for each of the series. And you can apply the similar logics across different series. So that's another way of paralleling things. And also when you have the model, if your data really is large, then you can do distributed training as well, trying to kind of utilize multiple machines to expedite your model training process. So yeah, so there are a lot of things can be done for the data, for big volume of data. So this is another way that we are thinking about, we need a framework to do this thing. Okay, so that's why we want to build a framework, try to do things systematically and in an organized way. Then how we build the framework, the next part is. So the first thing is let's try to think about if a data scientist is tasked with building a time series model, how she will do that. So basically, in the ideal situation, it's pretty much like the normal machine learning building process. You got some data, and people will run some analysis on that, doing something, figure out the characteristic about your data set. Are your time series are mostly like normal sort of a distribution, or they are more like intermittent distribution? So you need to apply some additional logics on top of that. And the next thing to do is, so we need to do a lot of feature engineering, derive useful things from those kind of time series inputs. Then we give it to a machine, try to get a model out. Then we do this kind of a careful back testing, trying to evaluate the accuracy as well as the stability of your model. Then finally, we get those things into production, and we make a business impact. So, but in reality, I think more or less the workflow is messed up, because we need to go very frequently between doing analysis and go to more feature engineering, go to more training, manage a lot of parallel experiments, and we need to do different types of strategy, evaluate, we need to change the metrics. And the model is never going to get into production because of this back and forth process. And it's very easy to mess up with things. For example, we have seen people are developing new features, but somehow these things are not taken carefully for the information leakage. So the entire evaluation process is actually do a done run. So actually the things that we derive are not so useful. So it can be easily it can easily happen in reality. So this is like pretty much what a human will do. And the framework is pretty much doing the similar things, but just trying to organize those things in a more systematic and streamlined way. So there are a couple of things that we are designing the framework to do. So the first thing, as I mentioned, is trying to streamline the entire process as much as possible, trying to prevent people going back and forth between those two different stages and mess up with things. The second thing is we design the model building process in a more declaration-based way. So in this case, if you are doing a model building process, actually, once you get a declaration of the things that you want to do, this declaration is going to come in as a whole configuration file and can be checked in to version control and can be tracked in a more easier way. So this is what do I mean by declaration. I'll talk more about that afterwards. And also, we support a large number of feature engineering and modeling strategies. So basically, the idea is trying to kind of enumerate all the possibilities, all the possible strategies that a human will do to derive the features, to try different models on top of the data set. We're trying to enumerate all the possibilities of doing that. And during the model building process, we're gonna just let people to choose, okay, here are tons of things that I wanna try, and let's do it, and let's see what happens. So people do not need to go back to try more things. So this is another thing that they wanted to achieve. And we also do this evaluation in a more automatic and correct way to evaluate the accuracy and robustness on the multiple forecasts. So the back testing thing is very critical in this situation. So it can be easily messed up. So we make our framework to do this correctly, so people won't make errors and trying to get things that shouldn't appear in your inputs into your model. So this is for the evaluation. And also we designed this framework to allow more or less distributed execution or running this entire process on different containers on the Kubernetes cluster to speed up the entire process. So these are some of the high-level features of our framework. Then I'm going to talk about more details about it. So the first thing we mentioned before, we designed the entire building process, model building process, as a declaration-based process. So what I mean here are two critical things. One is we want our data scientists to declare the characteristics about our data set. So basically, they're gonna tell the framework where the data is located and what does the data look like. So for example, there can be some columns, which is ID of a product, and there can be some time-based columns. There are some sales, there are some like unstructured or structured or real value data associated with that. We're gonna let people to tell us what do my data look like. So this is the first thing we need to declare. And the second thing we need to declare is what types of feature engineering and a model building strategy we're going to try on top of this data set. So people will tell us like what type of feature they want to include, how they want to do their robustness evaluation, how many variation of the forecast they're going to try, what type of model they would like to try in this building process. So this also comes as a YAML file. and people going to declare to the framework. So once we get those two configurations, then actually we got the entire building process described in those two files, and we are ready to kind of roll out the model building process. And in reality, also we find it's useful. People might not, because it's a very large configuration file. We find it's also very useful to have people have a initial version of the configuration. So actually, we have a functionality to automatically generate a configuration file from different featureistics about your data sets. For example, we're gonna examine like, okay, how many or what percentage of the series in your data set going to look like this one versus like those normal things. And we're gonna try different, we're gonna select the different metrics to evaluate those different models, because definitely the strategy to evaluate the bottom one versus the top one are going to be different. So we have some rule-based things that are going to examine those things and generate an initial version of the configuration for our data scientists, and people will just modify things as needed on top of that, and this is going to be fed into the framework as ultimately. Yeah, so once we got those two things, declarations about your data, declarations about your building processes, then we're gonna feed those things to a Kubeflow pipeline. So this looks pretty complicated, but on the high level, it's basically just trying to kind of fetch all of those kind of different types of data. And we're going to try several branches of a modeling strategy. Some of them are going to be traditional time series models. Some of them are going to be a machine learning based by sliding the data set into several sliding windows and trying to derive a model on top of that. And finally, we're going to kind of like compose a different report for each of the individual models and compare different things and combine those things together. So once everything gets executed, a automatically report will be composed, and people can examine how does each individual model is going to perform, both in terms of the accuracy and in terms of the robustness as well. So this is the high level sort of process that Kubeflow pipeline is going to help us. And in addition, there are computational resources going to be started during the entire process, and this is going to be managed by the Kubeflow pipeline as well. So this is a high-level process we're going to do. And if we look at a more detailed level, so we mentioned like, okay, this thing is basically kicking off several different model and data engineering strategy. If we look at it in a more careful way and more detailed level way, we also do the multi-node execution things by utilizing a distributed computing framework called Dask. So unlike Kubeflow pipeline, which is in charge of the high-level orchestration about different things, Dask is more dedicated to kind of scale our computation across multiple machines at the actual execution level. So for example, we might have a data set look like this. You have different products and you have different observations at different dates. Then basically, if you look at the data engineering process, what we're gonna do is we're gonna kind of like derive new columns actually from those kind of sales input or sales series. Actually, you can sort of partition this type of jobs into several independent, I would say, workloads. So for example, you can, those derivation of different features from the same sales channels can be delegated to different machines. And also you can do this kind of like a horizontal kind of a chunking of your data set by letting each individual machine handle like a chunk of the data, which may contain a subset of the products that you have. So for this particular example, actually, we can divide the entire feature engineering, for example, into 4 chunks of the data. And these 2 4chunks can be assigned to 4 individual nodes that is going to be managed by a Dask cluster. So this is another way kind of on the execution level. How do we speed up the processing of the data feature engineering process? And how the Kubeflow comes into play is it's going to serve as a high-level orchestrator, which is going to talk to a Dask operator, which is going to manage this type of persistent or on-demand cluster for this particular job during its life cycle. So this is what do we do for the data processing process. Another thing we do multi-node execution is for the training. So once you got the data ready, if usually like we do single node training if the data set is of a reasonable size, but there might be cases where we got a really large data set. Then usually like we do multiple node training under that synthesis by slicing the data into different replicas and having like each individual node handling some parts of the data and building trees on top of that. So yeah, we use like a tree gradient boosting type of model very heavily. So what it will do basically is going to, each node is going to take some replica of the data and going to build trees independently, and they're gonna exchange information about that to the master, and the master is going to kind of orchestrate the high level things. How do you kind of combine those different trees and trying to kind of get a final tree built out, which can do your prediction. This is another thing that we utilize Dask cluster to do multi-node execution. Yeah, so all the above things pretty much describe the way of building process, the model building process. How do we get a useful model? So basically, I think the idea is pretty simple. So basically, we are trying a lot of different strategies doing data and features, and we try a lot of models, and we look at which one performs best. So that's a basic idea. And then we make sure that we can utilize different nodes of the machines, and so we can run this entire process pretty fast. Then let's talk about how do we kind of put this entire process into production. So if you decide, okay, one of the model, I'm going to try this particular, I'm going to put this particular model, this particular strategy of doing feature engineering into production, what happens next? So basically, our entire process of model building can be described in a direct acyclic graph. So if we think about this, you might have a data set which contains 2 columns, and you're going to apply different types of transformation on top of each of the columns, and you're going to feed those kind of a process columns into several models, because we have we are doing essentially a searching process. We do have several models in parallel executed during the model building process. But these are not going to happen when you are putting things into production, because a lot of things are redundant. So you don't want to run kind of like 10 models when you want to doing your, I would say, like prediction in production. So and then what are we going to do is first we're going to kind of a record or keep record about all those kind of different transformation process, and some of them are going to be stateful, while other things are going to be stateless. For example, stateful means like these transformations come with parameters. For example, if you look at a categorical encoder, because like it needs to record like the actual relationship mapping from your human readable label to the machine readable label. So it comes with parameters. So these need to be packaged together with this particular node actually in the DAG. And also, of course, those models, they come with parameters. How do you kind of construct those decision trees? These are all parameters going to be shipped with this particular node in the DAG as well. And there can be other stateless node, for example, like if you are doing just a rolling transformation, if you just get like a rolling mean for your past data, these things are not going to be come with states. So basically, you just need to kind of compute things on the fly. So yeah, so you all have a DAG, which consists of different types of blocks. Some of them might be stateful, some of them might be stateless. But most of the time, if you decide, okay, I'm going to go with this XGBoost model, a lot of things are going to be redundant. So for example, there might be column 2, this particular feature, when we inspect the feature importance, it might play a very minimal role in the final model that you have. So in this case, actually we will sort of start backwards from the DAG and trying to kind of train all those kind of redundancy or redundant blocks and trying to make this DAG from a graph into a tree like stuff. So you're gonna have a pretty like streamlined blocks of things which are going to be executed during your inference time. So when a new data comes into play, you're gonna use this kind of a trained version of the DAG, which basically describes how you kind of process your data into a ready to be processed format by the model, and you're gonna use this model to spit out some results from that. So this is how we're gonna to put this entire sort of model searching and data searching process into production. And there's another circumstances where people are more interested in online inferences. So online inferences is less common in time series modeling, because time series modeling, there's a heavy logic of data processing. And when you are talking about samples, so basically you are talking about the entire sample or entire history realization of the series. So it's less common that people will do online inferences. But in those situations, actually, we do have a way to do online inferences as well. So the idea is pretty much similar. We do this DAG trimming, and we got those different blocks, and we transcompile those different things into sklearn transformers. And we combine those things into a composite pipeline, which is going to serve as a callable function that can be embedded in a web service endpoint. So this is what we do for the online inferences. So yeah, so this is how we put things into production after we get a useful model from our framework. Some other details, actually, or some other practices that we do. The first thing, we run everything on Kubernetes. We use the AWS EKS as our Kubernetes distribution. And we do have a ASG, automatic scaling group of Spot instances to run all those transient workloads. So actually, if we look at the cost of doing like very complicated things like that, actually the cost is pretty reasonable for our situation. And also we mentioned we use Dask for execution level, multi-node distribution a lot. So we manage all those Dask clusters through an in-house CRD operator. And with the framework, through our experiences doing business with our customers, the average time to ship a useful time series model is just 2 days. So we can get like a version 0 or version 1 of the model really fast. And usually like people can get an initial result just in 2 days, and we will tune the model on top of that. And we try our framework to do the Cargo M5 computation, which is a public data set or public computation in time series model prediction. And we can achieve 5% percentile with some level of tuning. I need to agree, actually, yeah, we need some tuning to achieve 5% percentile, but considering like the effort you spend on those tunings versus trying to write your entire process doing this kind of different modeling strategy and data strategy, this is a pretty minimal as well. And our framework is pretty elastic. So I think we have experiences handling data sets which contains 1 million products and 3 years of realization. So this is actually a very, very big data set. So usually like people won't do it in a single machine. So here are some other experiences and details, and also we get from this process. That's pretty much what I want to cover. How we do this time series predictive modeling at Convect AI, and we are looking at several things to do as the next steps. First thing is I have to admit it, this tuning process. So we mentioned this configurations. We pass into the framework. So even like we have an automatic way of generating like a scaffold of the configuration, we still need a lot of domain knowledge trying to kind of figure out the right strategy to do the data processing and the model building. So we need to build a smarter way of doing that. And also, we are also thinking about integration with some other parts, potentially experiment management framework, as well as the auto-tuning framework, trying to kind of make the entire process more organized and a smarter way of doing things. So here are some of the things that we are thinking about to do next. And that's pretty much what I want to cover today. And you can check about more things on our website, and you can contact me through LinkedIn as well if you feel interested.